Hi. So last time we start our station with a function. So today I'm going to continue the same topic, and what we are going to do today is we are going to try to go over some concept. First, we have to show that. So first, we are going to try to show that this function that's described as follow, is a one-to-one function and onto. And also we're going to find the inverse of that function, and we are also going to try to find the relationship between left inverse and right inverse of a function, and also between onto and one-to-one function. So we are going to cover this, and then we are also going to try to show one example with just one single real number. So from the set of real number to the set of real number, show how to find the inverse of this function. I assume we can prove easily that this function is one-to-one and onto. And then we are also going to try to show this example. So we have a function f defined from a set A to a set B, and the function j defined from the set B from the set C, and the goal is to show that if j on f is one-to-one, then f is one-to-one. So we are going to show this. And then we have one example here, the function q that's defined from the power set of b to the power set of a, such that q minus 1 of x equal to set of k from in the power set of b, such that q of k is in x. So where x is a subset of q of the power set of b. So the goal is to show this expression. So this is a union. So this is a union. And then we are going to try to again go over some detail about some key concept of the homework, some confusion that you may have, and also give you some hints on how to start. So let us just start with some key concept. So if you have a function that's defined from the set x to the set y, in this case x is the domain and the y is the codomain. To show the function is an injection or one-to-one, we must show that for all x1 x2 in the domain, which is this case x, if you have f of x1 equal to f of x2, this imply x1 equal to x2. So this is small x, don't confuse this. So this is x1, and we are going to see the case where if this was a cross product, so if this was something like x cross x, we're going to see how to handle that in the next slide, few slide. So if this was something like a x cross x, this cross product, it should be different on how to define this. So let us, for now, let's just consider this. So to show that the function is onto one-to-one, you show that if x1 and x2 are in x, f of x1 equal to f of x2 imply x1 equal to x2. And to show the onto part, which is what they call surjection, so we must show that for all y in the codomain in y, which in this case is y, there must exist a certain x in the domain, which in this case is x, such that f of x equal to y. So these are very key concept, a very key definition that we use it quite often, and this is also going to help you on your proof. And to show that the function is a bijection, you must show that it's a one-to-one and onto. So for the bijection, you just need to show that if for fully condition A and B respectively, or vice versa. You can choose to prove condition B first, then condition A. It depends. The order doesn't matter. So again, to show us a bijection, you must show that's an injection and a surjection. That said, you need to show us one-to-one and onto. So let us just pick one example here. So what I was saying earlier is that remember, if you have A cross B, we said that was a set of A, B, such that A is in A and B is in B. So we saw this definition earlier. So but the problem here is our function is not only defined from one set, it's defined from the cross product. So the function defined from the cross product, so we have to consider something like this. So in this case, because it's the cross product, have to deal with the pair. So in this case, if you want to refer to the definition that we have here, if you want to refer to this definition, of a one-to-one function, in this case x1 and x2 are going to be represented by a pair of elements. So in this case, we can think of x1 to be this first pair, which is m1 n1, and x2 to be the second pair, so x2 is m2 n2. So that's the definition. This is because we have the cross product, so we have to think of the pair of elements. So that's how it works. So remember, don't get this. Students usually have this confusion when we have the cross product set like this. That's why I decided to pick this particular case, so you can visualize. So again, to show that f is 1-to-1, which is again this notation 1-to-1, you must show that for all pair of element m1 n1 and m2 n2, just like x1 and x2 in the cross product. If we have f of x1 equal to f of x2, this implies x1 equal to x2. So it's just like in this definition, this is like this part is what we have here, this part, and the last part, which is this part, is what we have here, right? So to prove that, we just have to consider, so you assume f of m1 n1 equal to f of m2 n2, and you must show this part. So you assume this to be true fact, you try to show this. So how to proceed? So because we assume this to be a true fact, what we are going to do, we're just going to be replacing this value in the actual function. So this is how the function defines. So f of mn equal to m plus n m plus 2n. So if it's m1 n1, just replace m by m1, then n by n1 in this expression. That's how we get that expression that we have here. So basically, if you have f of m1 n1 equal to f of m2 n2, you replace it, you get this expression. And because it's a pair of element, you can just set this equal to this, which is this part equal to this part, then this part equal to this part, and you get this expression, right? So you call this 1 and this is 2. And if you subtract, so the question is, you're trying to solve this system, we're trying to solve this for m1 and n1, m1 and m1, yes. So basically, I'm trying to subtract, I'm going to subtract the top from the bottom. So I subtract 1 minus 2, I get this expression, and I can simplify, it gives me this. So m1 n1 equal to n2. Then if I replace in 1, if I replace in this expression n1 by n2, so if I replace this n1 by the value which is n2, I'm going to have n2 and n2 here, so I can cancel. Then the remaining part will be m1 and m2. So you get this. So from there, we are able to find. So we were able to find that m1 equal to m2 and n1 equal to n2. So that concludes our proof, because we was trying to show that if these two are equal, then this equal to this. So we assume this to be equal, which is this equal. Then we went up to getting the last result, which was this are equal. Okay. So and for the onto part, a function is onto, so f is onto if for every y1 y2 in the codomain. So be careful, this is the codomain because this can be different than the domain. So in the codomain there must exist, this is very important, there must exist a certain mn in the domain, this is the domain, such that f of mn equal to y1 y2. And again I said that for all y1 and y2 this must be in the codomain, and we are trying to look for something in the domain such that f of that thing give us the y's that we have over there. So we just go from this expression and we are going to solve for mn, because we are trying to find the existential. Because we pick any random y1 y2, we try to see if you can find, because of the existential, if you can find mn that fulfill this condition. So from there you get we have f of mn equal to y1 y2, and then from that we can, okay, so from that we get this expression. So if you solve, look at this note, you can just look at that, you are going to solve it and you should be able to get the result. It's very simple. So we get this from there, from this expression. So we get what we have here, f of mn equal to y1 y2, and we set this equal to this. Again, using f of mn we can compute this. So this equal to this expression, then you set this part equal to this part, then this equal to this, you get this system. And we can just solve it as we did previously. So you say 1 minus 2, you get the expression, and then from there you can just solve for n. So our n give us y2 minus y1, so we get the n here. Now you can, what in because you already have m in this expression, you can replace m in 1 to get n. So you just replace in 2 or in 1, you just get m equal to this expression. And so you get m equal to this, so you replace, you go back, you get this. So that's very easy. So you have mn equal to this expression. And the way to verify, so we was indeed able to find mn, but you still have to verify that they are in the domain. That's why we have to check this first parameter, and it's indeed in the domain because it's the sum of two real numbers. And again, is this one part is in the domain, again sum of two real numbers. So this indeed is in the domain of the function. So therefore we were able to find mn in the domain, such that when we apply the function on that, we get the image in the codomain. Now to find the inverse of that function, so the question is you're trying to find the inverse. So if you work your math right here, what you do, you just replace basically m y1 by m and y2 by n. So you just replace it, you get whatever you have here. You can see that it's just basically this expression that we just replace y1 by m and y2 by n. So basically we just get that type of expression. Now another example, which is the simplest case. If you look at this function is very simple. To find the inverse of that, what you can just do, you just said yeah, I assume you can prove that this is 1-to-1 and onto. This is very easy, you can prove this. It's easy to show that it's 1-to-1 and onto, therefore it's a bijection. So we can find the inverse. We want to find the inverse. What you can do to find the inverse, you just set f of y equal to f of s equal to y, then you solve for x. So when you solve for x, you get whatever you have here. And to get the inverse, you just replace this by x in your function. So you can just see that basically we solve f of s equal to y, we solve for x, we get this expression, and in the inverse we just basically replace y by x. So this is our inverse. And most of the time, if you have a function that's defined from A to B, most of the time the inverse f minus 1 is going to be defined from B to A most of the time. So that's how you get the inverse of that function, and it's very simple. So basically it's like you solve f of x equal to y, you solve for x, then you replace y by x in that function to get whatever you call the inverse of that function. Now another example of the composite of function where to deal with the one-to-one function. So let's say we have a function f which is defined. So f is defined from the set a to b, and j is defined from the set b to c. The question is, we ask that if j wrong f is 1 to 1, then f is 1 to 1. So this is the composite of function, then f is 1 to 1. So what we are going to do is, because this is a no fact, because we know that this is 1 to 1, the goal is to prove that f is 1 to 1. And to show that f is 1 to 1, so f is 1 to 1 if f of a equal to f of b imply a equal to b. So because this is a true fact, I'm going to assume this, then try to get this expression, right? So I assume this. So from assuming that f of a equal to f of b, I can just apply the composite on both sides. So this means j of f of a equal to j of f of b, right? And because this is a one-to-one function, so this is the same as saying that j wrong f of a equal to j wrong f of b, right? And because this function is a one-to-one function, j wrong f is 1 to 1, that means if you have j wrong f of a equal to j wrong f of b, this implies a equal to b. So this is done. And this was easy because j was a one-to-one function. So you were able to go from the fact that f of a equal to f of b to show that a equal to b. So this is done, right? Okay. Then I have another problem here. So we have a function q which is defined from the power set of b to the power set of a such that q minus 1 of x equal to set of x such that x is in the power set of b, and q of x is in q of k is in x. Now we have x a subset of the power set of b. The question is to prove this expression. So if you look at that, because x, we say that x, based on this definition, x is x is in this is a subset of so x is a subset of the power set of b, which is the power set of b. So if you pick the power set of b, so x will be somewhere here based on this definition. So this x will be somewhere there because it's a subset of the power set of the q of the power set. So because the function defined from this to this, so q of this power set should be something in this set, right? You get that? So you can get f minus 1 of that set is going to be something in p of b. So this is just for visualization purpose. You don't need to do this, just to visualize. Now, so to show that this is a subset of this part, so to show that this part is a subset of this part, we consider something in this set and we show that it's in this set, right? We saw how to show that. So we say let a in this set, we must show that a is in this. Because a is in this set, that means there must exist a certain k, because q is a function, and to get whatever you have q of this, right, it should be it's a set, right? That means there exists something in that set such that in that set, so it belongs to that set such that q of k equal to a, right? So this definition, this transition is very important. So I say that if there exists a certain k in the union of q minus 1 of x such that q of k, it gives you a, right? So if you have this, then because the k is in this set, you have k in this set, right? So you can say that k is a q minus 1 because this is a union, right? It's a union of the set, and it's the same set here, it's not changing. So we can say that k is in the q minus 1 of x, which is defined as follow based on the problem setting. So the problem setting is defined this way. This is how the q is defined, right? So we just use the definition of the q here. So k is in q minus 1 of x, which is defined this way. So this implies k is in the power set of b based on this definition, right? So k is in the power set of b and k is in x, right, based on this part. So the first part allows us to write down this, and the second part, this part, allows us to write this part, right? Then when we pick that, so we have a k in the power set of b and q of k is in x. So however, we saw that we said earlier that q of k was equal to a. So we have a q of k equal to a. This implies, because q of k equal to, so q of k is in x and q of k equal to a, this implies a is in x, right? And therefore a should be in the union of the x. So we conclude our proof here. Now that was another very tricky proof that you also have to master, and that will help you on some question on the homework. Now additional concept of injection and surjection. So basically I got this from your lecture note, and it's very important. You have to review this, and that can save you a lot of time when you are trying to do some kind of tricky proof. So we have the if f is surjective or is a surjection if for all s as a suggestion. So f is from f is from the set a to the set b. So for all j and we have the function s from b, there is a certain age such that s is defined from s to a and j equal to f from j. So this, you can look at this in your lecture note. I just got it from a lecture note, so it's very important that I mentioned that you can take a look. And another thing that you have to notice is that when you call we set a function bijection, we had to show us both injection and surjection, and we saw that how to show this. So basically it's saying that we have to show us one-to-one and onto. And when it's a bijection, that means we have the inverse. So to show us function and then it's inversible or have the inverse, we show us one-to-one and onto, or we show us functions have a bijection. It's a bijection. So for the right inverse, if you define the function f from a to b, so f have a right inverse if there exists a certain function. So look at this. There is a certain function j from b to a such that f from j equal to identity of b. And similarly, f have a left inverse if there is a certain function h from b to a such that h from f equal to identity of a, right? So again, these are some very key concepts that you are probably going to need on your homework or even in the exams. And I really encourage you to fully read the material and do your own particular research on this class, because it's there's a lot of concept and I cannot cover everything on the station. So you have to try to watch the lecture note and also go over the lecture note, the lecture video recorded by the professor. So that will be very helpful. So and here this means this like double implication. Again, double implication. These are some key concepts that you have to know, and this can save you sometimes when you are trying to prove. So we are saying that if f is onto, then f have a right inverse. So this basically this part, if f is onto, then f have right inverse. So If we show that this function is onto, we can conclude the have right inverse. And if the function have right inverse, then it is a surjective. So basically, if f is 1 to 1, for example here, f is 1 to 1, this implies f have a left inverse. So that's just some key concept that you have to know. Now that's it for what I have today, but let me go ahead and give you some hints about the homework, and hopefully that will help a little bit to clarify some stuff. So the first one is for the first question, for the question 1, we are given the set A, which is the set of xy, such that x is between 2 and 4, and y is between -1 and 3, right? So I suggest, depending on how you visualize stuff, but this is going to help a lot. So this is 3, so this is the y value that we need, and so this is x, this is y, and for the other part we have a 2, 4, this is 2, and then 4 here, so this area, right? So basically this is the area that we need. So we need to compute the image of this area. Okay, so that's what we need, and this is 4, 3, this is 4, this is 4, -1, this is 2, 3, this is 2, -1. So that's just the area that we need. So we are trying to compute the image of that area. So to think about how you can figure out that, so basically you can find a way. You can always have the boundary also, like we have like we specified the set. So think about how to proceed, but that's the hints. And then another thing that you have to be careful of is on question 06, for example. On 06, we are given a AF, which is a set of function. This is a set of function from the natural number to the natural number, such that f minus 1 of A equal to the empty set. And I assume that for B you're going to have similar expression, B from n to n, such that f minus 1 of B equal to the empty set. So again, and then we have something like this. This is A, this is B, this is n, right? So, and we say that if you have f, the question is to prove that Bf is a subset of AF, right? And be careful, because these are functions, so we must pick a certain function in this set. So you must pick f in that set, and then show that f is in AF. And to show that f is in AF, you must show that this f that you pick in B, because B is described this way, this same f should be in this set, right? I'm not certain about this set B, but for A you are given, but I assume that for B it will be something similar. So that's what you have. And another thing that you have to consider is in 05, for example, in 05, so you have a function phi which defines from B cross B to the power set of A cross A. So remember, B cross B is a set of A is B1, B2, such that B1 is in B and B2 is in B, right? And A cross A is a set of A1, A2, such that A1 in A and A2 is in A. So just to let you know, in case you need to use something that is from this set, you have to think of as a pair of element. If it's from this set, it's a pair of element like you have here. If it's from this set, you need a pair of elements. So you have to recognize that, because that's very useful to do some proof. And I think that's what I have for today, and hopefully this will help on your homework and you help you better understand the material. And please make sure you read the lecture material and also watch the videos that are posted on Canvas, so that can help you to better understand some concept of this class. Thank you.